following is an example of solving a second-order differential equation of the type that's an initial value problem. So here we have the dE second derivative of y with respect to x plus 2 dy dx minus 3y equals 5e to the 2x. And it's an initial value problem because we also have y naught equals naught, y dash naught equals negative 2 specified as initial conditions. And the first thing we do is find a general solution for the second order dE. Then we substitute in those initial conditions. So the first step with any second order linear dE of this form is to start by finding the auxiliary equation. And in this case, that will be, because we have second derivative of y with respect to x plus 2 dy dx minus 3y, the auxiliary equation is going to be r squared plus 2r minus 3 equals 0. And we solve that for r. And in this case, that one is going to readily factorise as r plus 3 times r minus 1 equals 0. So therefore r is negative 3 or 1 in this case. And these roots of the auxiliary equation determine yh, the complementary function, which is the solution of the associated homogeneous dE. And in this case, these are two real distinct roots. So the form of the complementary function yh is arbitrary constant a times e to the negative 3x plus another arbitrary constant b times e to the 1x. The next step is we then need to look at the right-hand side of the dE we started with. And in this case, this is 5e to the 2x. So it's the e to the 2x bit we're focusing on. That is of the form e to the px, let's say. And what is important is whether this number 2 is a root of our auxiliary equation. And if we look at the roots of our auxiliary equation, they were negative 3 and 1. Neither of those roots were 2. So therefore, because the right-hand side is 5e to the 2x, and this 2 is not a root of our auxiliary equation, that means that we pick a particular solution or a particular integral yp, which is just of the form c e to the 2x. And then the next step is to differentiate this. So the first order derivative of yp with respect to x will just become 2c e to the 2x, and the second order derivative of yp with respect to x will be 4c e to the 2x. And we want to find what c is. Now, these must satisfy the dE. That is, they must satisfy second derivative yp double dashed plus 2yp dashed minus 3yp equals 5e to the 2x. So therefore the next step is to substitute yp and its derivatives into this, which in this case will become 4ce to the 2x plus 2 times the first derivative, so 2 times 2c e to the 2x, and then minus 3 times c e to the 2x, and that is all equal to the right-hand side of 5e to the 2x. Expanding and simplifying, all of these are multiples of c e to the 2x, which expand to give us 5c e to the 2x on the left when we simplify, equals 5e to the 2x on the right. The e to the 2x's cancel, leaving 5c equals 5, hence c is just equal to 1 in this case. So yp was c e to the 2x. In this case that will just be yp is 1 e to the 2x. That is, yp is just e to the 2x here. So this is what we have found so far. The complementary function yh and the particular integral yp. And the general solution y is then yh plus yp, which in this case will give us y equals ae to the negative 3x